Okay, so now we need to figure out which of the 1100 characters are overriding the save return pointer and thus causing this crash in EIP. So what we want to do is create a cyclic pattern, and we're going to do this in Immunity Debugger. And we do our commands down here at this white part at the bottom, but that's kind of small, so I will put them in Notepad first so we can see them a little bit better. And we do, of course, need to restart WarFTP. It's currently crashed. Some programs we can do this inside of the debugger. That will not always be the case. Sometimes you'll have to detach and restart it. But with this one, we can go to debug and then restart. Say yes. And seems to have restarted nicely. If you do have any problem with it, it may, in a few cases, I'm not really sure what it is that does it, because I can give people the same VM and most people don't get the error, but then a couple of people do. But if you do get an error and it says like unknown database format or unknown username format or something like that, it'll just put up an alert window that says that. If you go into the WarFTP folder, there will be a file ftpdaemon.dat, and if you do get that error, just delete it before you restart. It just deletes the database. And if you don't get it, then you don't have to do that. You can just restart like we did. But if you do get that error, and if we do get this error in a later video, then I will show deleting it. But just in case you get it, you can just delete that file and everything should be fine. So it does pause when you restart. So we see pause down here, so we can click play. And where did my WarFTP go? It says it's running, but it's not there. Alright, so let's just say restart again. And hit play. There we go. Unknown file format or user database. Cool, I got to see it. Alright, so we got to say OK here, and let's delete that ftpdaemon.dat. Again, you probably won't get this, but luckily for the state of the video I did, so you can see how to get rid of it. So just delete the .dat file, ftpdaemon, and now go to restart, and it should restart fine. Cool. Click OK, click the lightning bolt so it's running, and we're still attached to it in the debugger. So we should be good to go. Alright, now we need our command to create our pattern. So we're going to use a add-on called Mona, and it is added on to Immunity. It's not in there by default. You can just download it and add it to Mona. We did that, or add it to Immunity rather. Add Mona to Immunity, and we did that in section 1 when we did our setup. So we want !Mona pattern create. We'll use Mona a fair amount in this class as we do the exploit development. It has commands for a lot of useful tasks that make exploit development a bit easier. So we want to tell it to create a 1100 character pattern. So we're going to replace that 1100 A's with this pattern that is going to allow us to see where our save return pointer overwrite is in just one step instead of having to break it down into multiple steps like I showed you in the previous video. So I'll just paste that in. So Mona pattern underscore create and 1100. And since I set up the logs when I was doing this setup, it does log it to clogs war-ftpd pattern.txt, so it's clogs and then the name of the program it's attached to, and whatever the command is. So if I go to the desktop, not the desktop, that's where everything else is, clogs war-ftpd and then pattern.txt. There's our cyclic pattern that's 1100 characters long. So I'm going to copy this and move back over to my Kali VM, and I'm going to use nano and edit this warftpscale.py. And I'm just going to comment out buffer equals a times 1100, so that'll be a hash in Python. Then I'll recreate buffer. You could also just get rid of that line entirely or delete the a times 1100 and then redeclare it. But this is nice because we can see each step as we move through it, so it'll be nice to remember what we did, because I am going to have you do an exercise where you do this yourself, so it'll be nice to have all the steps. Alright, so I'm going to say buffer equals open quotations and then paste in that 1100 characters of the cyclic pattern. And don't forget the close quotations at the end. Whoops. Mine ended up on a second line. That's no good. So it should light up green in Nano. Alright, so instead of 1100 A's, now we're going to still send it 1100 characters. So the link should be the same. But now we have our little cyclic pattern. You can kind of see how it works. Big A, little a, 0, big A, little a, 1, so on and so forth. You know, we get a little B and a little C. So you can see it could be pretty long before it has to loop around. So go ahead and save that. That's the only change we're going to make here. We're just redeclaring the buffer variable to be our cyclic pattern so we can crash it again. So make sure we are running over here in immunity. We are indeed running. So we should be good to go. So over at Kali, let's run it again. Get the same output here. So everything as expected here. It said, hi, I'm the WarFTP server. Please enter your username. Please enter your password. So we do, or the script does rather. So if we come back over here, we get access violation when executing, this time not 41, 41, 41, 41, since we didn't send it a long string of A's, we sent it our pattern. So instead we get 32, 71, 41, 31, and it's here in EIP as well. We can also see parts of our pattern in ESP, EVP, and EDI. Those were covered in A's last time, so that is to be expected. So what we can do, we have a couple options just to see what is in EIP. We could just do exclamation point Mona pattern underscore offset and then give it 32, 71, 41, 31. And it says that that piece of the pattern is at position 485, so it's 485 bytes into our attack string. But remember that, go back to the CPU view, we also have these registers that have been overwritten with part of the pattern. And I mentioned that that might be useful as a place to put our shellcode. So we can actually just do one step that will allow us to see all of the places that the pattern shows up in memory. So we can do Mona find MSP, so that's find Metasploit pattern. This cyclic pattern is part of the Metasploit framework. You can also use Metasploit to create it directly on Kali, but I typically use Mona for these sorts of things. Alright, so we can do a Mona find MSP, and we do have to crash it with the cyclic pattern in order for this to work, so we do need to have our cyclic pattern in memory. Otherwise it won't find it, because it's specifically looking for parts of this pattern in different formats. So let's do exclamation point Mona find MSP. And it's going to take a little bit here. You'll see it says searching down at the bottom. It is searching through all of memory for parts of that pattern. It will just take a minute or two for it to finish. So this will again give us the location of EIP, but it'll also find what's in our registers and any other place that happens to be overwritten as well. So let's see what it comes up with. Alright, now it's done. So we can take a look again at the output. So if we go to C logs war-ftpd, this one's called find MSP, so the files are named after whatever we told it to do. So here at the top we have all of the loaded modules for this one. So these are, you see some Windows DLLs that are loaded, and we also see WarFTP itself should be here somewhere. Like here's WarFTPD executable. It looks like it also has a DLL of its very own. And you see information about them, like their base, the size of them, whether they're rebased or not. So that basically just means whether or not they can move. See, one of them is rebased. And things being in the same place every time certainly makes exploits more stable. I'd be able to use them on other platforms, for instance, or at the very least on other Windows XP Service Pack 3 systems. So we generally like to look for things that don't move or don't move very often. And safe SEH, we will look at structured exception handlers, or SEH, in a later portion of this exploit development section, but they're not really relevant now. Notice that a couple of them do have safe SEH as false. That will certainly come into play. Address space layout randomization, or ASLR, that's false for all of them. That didn't come in Windows until Windows Vista. That said, it isn't a requirement that you use ASLR on your programs, and certainly legacy programs like this wouldn't have it enabled. So ASLR, or address space layout randomization, is another thing that makes things move. Anything that does have ASLR enabled on an operating system that does support it, so Vista or later, then it would, when you reboot, all of those DLLs, all those programs would be loaded at a different space in memory. If you continue with exploit development, you'll see ways to bypass ASLR. It is certainly relevant these days, but again, with this example and anything we're going to do in this class, we won't see that. If you take an exploit development class, I'm sure that will be covered. It's certainly covered in mine, but for now it's not relevant. Likewise, no execution. We don't have to worry about that here. So data execution prevention basically, again, is a way to stop exploits from working. So it's like, oh, we're executing code off the stack. Why are you executing code off the stack? You shouldn't be executing off the stack. The stack's just supposed to be like local information. It shouldn't be executing. So someone got the bright idea, well, let's just mark sections of memory that aren't supposed to be executed as not executable, and then people can't just put their shellcode there and execute it. So again, if you take an exploit development class, I'm sure you'll spend lots of time looking at different ways to bypass no execution, but we don't have to worry about it here. We don't have an X on. And it also says, are they operating system DLLs? And that's true of everything that is not WarFTP itself or any of its DLLs. So operating system DLLs are probably going to change among service packs, or could even change just among a few updates, and certainly among different Windows versions. They're probably going to change. Not necessarily are they going to change. There are some instances of DLLs that don't change that often. In my experience, MSV CRT is a good operating system DLL that you can use. It doesn't change very much in the history of Windows, whereas something like User 32 or System 32 does have a lot of changes. It's bigger, a lot more going on. So if I have to use an operating system DLL, I usually go for that MSV CRT.dll, but just for this basic example, really any of the operating system DLLs will work just fine. We're working with this specific platform, but we would like, as exploit developers, to make our exploits as universal as possible. And so my first thing is I try and go for WarFTPD itself or any of its DLLs, and if not, then MSV CRT if it's there. So we'll see that a bit later on. Alright, then the actual meat of FindMSP, the program, looking for our pattern. So it found quite a few parts of the pattern, but in particular I'm interested in the registers at this point. So EIP, again, it found its offset is 485, and it did find those other three registers, ESP, EDI, and EBP, all contain part of the pattern as well. So ESP is at offset 493, and afterwards it has the length of 607 bytes. So if we put our shellcode in ESP, we have 607 bytes for shellcode. More space means we can use more advanced shellcode. Certainly helpful. Let's see, EDI is at 749, and its length is 351, so not nearly as long there. EBP is at 581, and its length is 519. So EBP has almost as much space as ESP. Chances are we could probably use EBP just fine, but let's go ahead and grab ESP. It does have the longest length, and as we'll see, it'll make something interesting happen that I think is worth seeing, particularly if you're going to continue in exploit development. So I will choose ESP. That's where we're going to put our shellcode. So its offset is 493, and that has length 607. I'll just go ahead and copy this out. Oops. FindMSP, and untitled is what I want. So just copy this for reference. So offset is 493 and length is 607, and I'll also just put the EIP is at offset 485. So we found that with find MSP as well as with the pattern underscore offset that just finds the IP. So that means our save return pointer overwrite is going to be 485 bytes in. And then it looks like, so save return pointer is 4 bytes, so that'll get us to offset 489. But then ESP is at 493. So if we remember our picture from the beginning of exploit development, it said that our saved return pointer was right on top of ESP. So why are we 4 bytes off? That's kind of confusing. Well, sometimes the picture is not completely exact. What's happening here is the calling convention. There's different calling conventions, different compilers that you use, different platforms. They have different ways of dealing with things. There's certainly no hard and fast rules that this has to be done this way. So basically the arguments, so there's one 4-byte argument between EIP's overwrite and ESP, so there's 4 extra bytes that basically get stripped off when our whatever function we called returns. So there's just 4 extra bytes there. So nothing to worry about. It just makes our picture a little bit inexact in this case. But this is going to be taken care of automatically. We don't have to worry about ripping off extra arguments or anything. When it compiles, it takes care of all that automatically. We just need to know ESP is at 493, EIP is at 485. So we'll just take that into account when we build our attack string. So next thing we need to do, of course, is verify that this is all true. As you become more familiar with exploit development, you may skip that part, but I encourage you to always verify everything, because as soon as you stop, at least in my experience, that's when you start making mistakes, and we'd rather catch them now than way down the line when everything just stops working and you can't figure out why.